is good. So, welcome everyone. Thank you for coming. This is our senior design project. This is it, basically. You all, after this, most of you are going to either graduate, or if you're not, you probably have very little to do with the engineering department, or you're just taking a couple Gs in the fall. So for those of you who are not very familiar with the process, these projects started about a year ago, right? Many of these guys started almost thinking about the project and what they want to do last May. So it's been almost a year. They have been kind of playing with the idea first and actually starting designing it and finally implementing and packaging it. So this whole process is a very, very lengthy process, and this is probably one of the most probably stringent aspect of the whole curriculum, to make sure that the students go through a very real projects that really, for those of you, again, just to give you a basic idea of what it takes to complete this project, each project must have an outside client. Each project must write a grant proposal in order to get money for the project. And in addition, each project must have an industry mentor. That means they have to go outside, they have to talk to someone who is currently working in industry and kind of get their blessing and make sure that they are, once in a while, they're in touch with them. The first part of this project was presented in December of 2014, which we refer to it as the kind of a proposal. So the students come up and they basically explain what it is that they like to do. Then in March, they had a midterm design review, basically telling the committee what they have done so far and what they have accomplished. And finally, today is the final design project review, which is after each presentation, the students will actually do a demo, and which they kind of demonstrate what they have done throughout the last 2 semesters or almost last 12 months. So we're really proud of them, and I know they really went through a lot of problems. Last night I had a phone call from the police department that we have like several students in the lab, and I had to call the police department saying that leave them alone, they're doing their project. So this was just one example of what they had to go through. There were a lot of issues that they had to deal with, anything from bad copy machine all the way to bad, maybe not being able to get to the buildings, not being able to get to the rooms, not having the right equipment sometimes. But in spite of all of these, I think everyone has done really well, and we're really proud of them. And every year, we really compare the quality of the works that students have done with the previous year, and we really see a significant difference in many different aspects, both the quality of the reports, the quality of the project as a whole, and also the engagement of students in various activities. For example, this semester, it was the first semester that every single group that is presenting the senior design project participated in the science symposium, which happened to be last night. The engineering department, instead of its smaller size, we had 10 different projects last night. So the only reason I said all these things is just because they're recording it, so I had to say that for ABET. So now, aside from all of these things, which they were all true, and again, I want to reiterate that this project that you see, although these students will have only 20 minutes to just talk about it, but it took a lot of effort, and it really, really took a lot of their time. And it was, if you had actually seen what they had to go through and the number of hours that they spent on these projects, it is really overwhelming. And in spite of the fact that we don't really tell them how proud we are of them, of what they have done, but seriously, this is really, and you will see after they present their demonstration that how much work that has been put in each one of these projects. So I will only go through each single project, and I will name the team members in each project, and after that I will go aside, and each team, in order that I'm calling them, will come here and present. We would like each project to be limited, each presentation to be limited to 10-15 minutes. Each demonstration to be limited to perhaps 10 minutes if possible, and therefore we like to kind of keep each project to half an hour, no more than that. If it takes longer than that, we have to cut you down, and then perhaps you can continue with the demo if it's okay after we finish with everyone else. So if for whatever reason something did not work, don't worry, we'll stay here after all the presentation and we come back to you. Okay. As a final note, please make sure that you give me your folder before you leave. I will look at it. I will return it to you. You need to make all the corrections that has been suggested by other faculty members. So please make sure you address those corrections and give the folder back by no later than next Friday. If you can give it back earlier, it would be better because you get more feedback. And finally, the survey, exit survey, for those of you who are graduating is extremely important. Please make sure Ronnie is actually emailing it to you. So please make sure if you are planning to graduate this May, please make sure you complete the survey and send it back. And finally, we do have the sweeping ceremony in the lab each semester. That's actually each May, which basically students are requested to basically get a sweep and just clean up the lab wherever you were. So, and they take pictures and we make sure they go on the wall. So with that, let me just introduce each group. The first group will be Artificial Doorman by Andrew Cradle and Maram Salama. The second group is Wired, which stands for Wireless Internet Repeater and Detector. We have 3 students in that group, Jonathan Perazzo, Campbell Smith, and Eric Zaro. The third team will be presenting their Laundry Now project. The team members are Frank Montfort and Ryan Russo. Fourth project is Weather Satellite Receiver by Alicia Afesi, Alberto Martos, and Joe Gordon. And finally, the last presentation will be Passive Wireless Pavement Sensor by Eduardo William and Arnolfo Puerco. So with that, I will introduce the first group to you. Good luck. Thank you.
So hi again. My name's Maram, and this is my
I'm Andy Kreidel.
Okay.
And this is our project, the Artificial Doorman. So the problem that we're addressing is that home safety and home security is a really high priority for all human beings, and especially people that live in dangerous areas that oftentimes can't afford a decent security system. And so we designed an extremely cheap security system with no monthly fees. And all the communication is over SMS and email, so it's extremely compatible with anyone that's equipped for modern life. And yeah, so we essentially what we wanted to replace was the concept of the doorman. So we equipped a door with a bunch of sensors, and we ended up with a product that makes the human doorman obsolete. And yeah, so what we did is we have a piezoelectric sensor and a Hall effect sensor and a motion sensor, and we'll explain how those are incorporated.
So there's similar product out there. There's a Schlage Nexia and the Ring Video Doorbell. They cost about from $250 to $300 with monthly fees, but as you can see, they don't really come with that many features as someone would want. But what we're proposing is a doorman that comes with a little bit more features, like text message alerts, picture snapshots and email alerts, remote locking and unlocking, and yes.
And so, like I said, the main goal of this was to make something that was extremely affordable, and the end price was somewhere around $160. And like I said, there's no monthly fees, except for, of course, you have to pay for your own internet and your mobile devices. And so, yeah. So this is a flowchart, sort of to walk you through how the device functions. So the onboard computer we're using is a Raspberry Pi. So what this does is it reads our sensors constantly so that it can send notifications to the resident and keep them informed of what's going on at their front door. So we have a PIR, which stands for passive infrared sensor, and so that takes in the infrared radiation from anyone that might be approaching the door, and that will trigger the camera. And then with that picture, we can send that through email to the resident's email address, and they'll have a picture log of everyone that showed up and exactly what time it was. And then we use a piezoelectric sensor to, which is sort of like a speaker. It creates current from vibrations, and so we read that with an analog to digital converter, and then with that data we can tell if someone's knocking on the door, and we can send text message notifications pretty quickly. It takes about 10 seconds if you're connected through Ethernet, and then we have a Hall effect sensor, which this is a little bit inaccurate. It would be, the Hall effect sensor is actually on the edge of the door. It's a magnetic sensor, so that you have a magnet on your frame, and the Hall effect will sense the electric field of the magnet so that the computer knows whether your door is open or closed. And then you can mess around with the settings if you want to, let's say, a lot of homeowners want to know every time their door opens. And then younger people just want to know if they left their door open for an hour or so. So that's how it works. Oh, one more thing. You can text message to the email address of the doorman, and then we have a program that will read the email, and if it receives the unlock command, which essentially would be a password through text message, and then it'll electronically unlock the door for whoever is there.
So here's a flow chart on the Raspberry end. As you can see, there are multiple sensors, and once either of them is triggered, the Raspberry Pi will send, so if the motion sensor is triggered, it will take a photo and then send that to the user's email. And then once they view it, the Raspberry Pi will wait for a response from them and then act accordingly, as either lock the door, unlock it, or just check the entry log and who's at the door. And then there's the user's end. So on the user's end, they're gonna receive an email or a text message. They have the choice of viewing it or just ignoring it. And then if they chose to view it, and then they will respond back to the Raspberry Pi with an locking command or unlock command. So here's a schematic of our design. Here's our H-bridge, and our locking mechanism is connected to it. The motion sensor, the analog to digital converter. I think this is the Hall effect and the piezo. And this is our button for when people want, well, if there's an unlock command and you want to, you don't want to wait to see if it's there, you can just push on the button and it will lock the door or unlock it.
Okay, so this is just a video demo of the project working. So this is, let's make it bigger. Oh gosh, what was that? All right, I'm sorry. You're gonna have to squint, ladies and gentlemen. So essentially what we have down here is a passive infrared sensor, and I'm going to lean down and trigger it so that we can take a picture. And then it's going to send a notification as well as an email. And it's in real time, so there's quite a bit of delay because there's not a lot of computing power here. And as you can see, this is the monitor of the onboard computer just running the program. And that's about how much delay you get, like 10 seconds or so. So it's fairly effective.
Yeah, there we go.
Oh, okay. And so this right here is the piezoelectric device. Or I'm going to explain it first. So right here we have the piezoelectric element, and like I said, that turns physical vibrations into an electric current. And so what we do is we feed that analog signal into right here is an analog to digital converter, and with that signal we feed it into our onboard computer, the Raspberry Pi, and we interpret that as a knock so that we can send a text message to the resident and inform them that someone's knocking on their door. So, a bit of delay, like I said, but it gets the job done. So we never got around to doing breach alerts, but that's sort of an extension of what we would like to have done on the project, because we have all the sensors in place to tell you whether the door is locked or not, and whether it's latched or not. And so if it's latched, or if it's unlatched but it's still locked, then you know that someone's breaking into your home, and so you can get an alert and act on that information appropriately. So I'm talking a little bit about the software we're using. I experimented with a lot of Linux command prompt tools, and what I ended up using was Mutt, which is a text-based user interface for email. And so that made everything pretty easy to do in the command line and then later in a bash script. And so that's how we can send the emails automatically with a little bit of latency. And then we are reading the general purpose input-output with Python libraries. And so we call this Python code from a bash script. And that's how the computer interprets all the information from the sensors. And we also needed I2C libraries because the analog to digital converter uses I2C as a digital protocol. So that's how the two can communicate. You want to talk about some challenging aspects?
So the most challenging aspects were working on campus was a little difficult. For some reason, some of our programs and commands wouldn't work over the network, and especially Matt was having a hard time. I don't know, but yeah, it was just not working properly over here, but when I tested it at home, it was like working fine. And another one was whenever the I2C was enabled, the camera would disable itself for some, I don't know, for really, it doesn't make sense why it would do that.
Yeah, so yeah, as it turned out, the model of the Raspberry Pi that we bought had something conflicting in it, where it could either use the camera or it could use I2C, but it wouldn't be able to use both
Together
without restarting it and enabling the camera module. Yeah, there's a bit of a design flaw there that we didn't anticipate.
Also, with the PIR and in snapping photos, it was a little difficult to figure out what the appropriate sensitivity so it doesn't snap pictures every whenever there has been a slight movement or a vibration. So yeah, it took a little while to figure out the proper sensitivity to snap in a picture.
Mm-hmm. And like Maram was saying, MUT works beautifully on everyone's home network that I tested it on. But when I take it to school, all my files get corrupted. I don't know, not much I can do. But I did get around that somehow. The thing crashed, and I rebuilt it all, and it works okay, except I can't call MUT from Python, so I have to do it in shell, and that wasn't really too much of an issue. So now we're going to talk about what we learned. We learned a little bit about diligence and hard work, and we learned how to apply all the stuff we learned, and most important, our ability to learn. And yeah, it was a fun project, getting our hands dirty.
So with funding for our project, we received about $500 from the IRA grant, and we also presented at the Science Symposium yesterday. Future work, what could we add up to our existing project? Maybe implement more sensors. I've tried working on video streaming, but it was a little difficult, and it had a lot of delays, so it wasn't really optimal for what we needed. And also, a user-friendly application would be really, really good to have.
Yeah. And also, as far as putting more sensors, this device could be expanded to provide security information throughout your whole house if you wanted to. Also, it could be, there's also different ways of sensing whether someone has arrived and to trigger the camera. So that would have been interesting to experiment with, maybe like a doormat that's sensitive to pressure. Because if you have a passive infrared sensor outside, it's gonna receive a lot of noise from the sun, and so you would essentially have to adjust the sensitivity constantly somehow, or else you would receive a lot of false positives, and that would be no fun.
So our faculty advisor was Dr. Jack O. He has received his PhD, Master's, and BS at Rutgers University. He's interested in RF and analog CMOS.
At this point, we'd like to thank our corporate sponsor, Digilock. Ben Valdivinos was an SSU alumni, and he was working for Digilock at the time that we started this project. And so he helped us out a little bit. He gave us a locking mechanism that was pretty easy to interface with a motor driver. I mean, we had to use our own motor driver, but yeah, it worked for a while until the wires came undone. Yeah, but now he's working for Fitbit. Anyway. That's our project, and we would have liked to show you the locking mechanism in action, but it's the cheapest thing I've ever seen, and it didn't even come with a data sheet, and it broke. So, yes. Thank you for joining us.
Any questions? Yeah, what will be the response of your system with, let's say, an animal which is in fact lower than the, the height is not that high for the camera to see or whatever?
So when we were experimenting with the sensitivity, there would be times where a cat or a mouse could even trigger it. But we didn't do a lot of testing outside, which is a shame. But also that would have been extremely difficult and time consuming. So for the proof of concept, that video demo is really all we got for you.
Yeah.
But yeah, that is a really valid concern, is that this device would receive a lot of false positives unless we spent some time testing and researching the best trigger for the camera.
Also, one thing that we could do is to program it so that it only snaps a shot if it sends a knock. So we can just have two options instead of just, oh, there's something that walked by, snap a shot of it.
Yeah. Another question that I have is that, do you have any interface to the, let's say, to the police and so on, if the owner wanted, be away and then wanted to, the system to automatically go to the police and so on, do you have anything for that?
I did a little research on that, and honestly, I wouldn't ever do that for a school project, because calling the cops is illegal if you don't have a real emergency. And besides that, there are some legalities to it, whereas you have to sort of be a major alarm distributing corporation to have automated calls to the authorities. Because, yeah, emergency lines don't like getting automated calls.
Okay.
Yes.
How about multiple recipients? Meaning,
Oh, yeah, that would be
so that's probably what he's looking at.
Yeah.
Sending it to two different people.
Definitely. Yeah, we can, that's really simple to implement.
Yeah.
Mm-hmm.
Any other questions? Okay, thank you. Thanks.
Good to go. Good afternoon, everybody. My name is John Perazzo. I'm Eric Zaro.
And I'm Campbell Smith.
And today we are so excited to share with you our project that we've been working on for the last year and show you what we got.
So we'll start with just a quick agenda of what we're going to cover today. We're going to start with the common problem that we're looking to solve here, how we plan on solving it. From there, we're going to go through how we tested and built our system, our acquisitions we learned, future outlook, and then we'll finish it up with the demonstration of what we have.
So first off, we're here to present our project results. First, we'd like to discuss an important event with our project that occurred last night when we were performing final prototype testing. So what you have here is a picture of part of our board at 5 p.m. last night. This is a picture of that same section of board at 8 p.m. last night when we accidentally triggered a catastrophic failure in one of our power systems. So as you can see, there was severe damage to a lot of the major components on our PCB. And it just goes to show you that, well, we learned a pretty hard lesson that no matter how hard you work and how much time you spend on something, there's always the possibility of things going wrong. And these things will happen, and you have no choice but to deal with them, whether it's the first day of the project or day 155 right before your final presentation. But we're happy to say this is what that same section of board looks like this morning as we're presenting. So if you trust your skills, there's no problem that can keep you from completing your project. And now we'll get back to the standard agenda.
So what we have here is a little simulation of traditional, so our initial problem that we wanted to address was a very familiar problem that everybody kind of runs into at one point or another, is the poor Wi-Fi connectivity in a dwelling or room. And so as you can see from this diagram, you have a source in the middle and you get a lot of shielding in regions like this because there'll be a lot of metal appliances or walls. And because of this, you get a lot of attenuation of your signal. And so to combat this problem, what we are implementing is basically a repeating system that takes your initial signal, repeats it, and addresses it to another person. And so therefore, if case 1 is our station, and 2 would be our repeater, and 3 would be the end user. And as you can see, this transmission carries out through a dwelling, gets to the end user. And though this is being implemented, and this isn't a new technology, what is new is the platform we are choosing to use, and that is a smoke detector. And so why we think this is a great idea is, as you can see from this simulation, it's another simulation we carried out. If you have this is a layout for a standard household, and if you have your office over here where your traditional Wi-Fi transmitter is, you can see that the signal is greatly attenuated across the home. In some of these other rooms, you don't even get any signal whatsoever. And so by implementing this design in a smoke detection system, you get flawless Wi-Fi coverage in every room of your house. And this is fabulous because you're integrating into a platform that's already there, power's already there, and it works phenomenally. So
we'd just like to cover a few of the similar existing products that are on the market now. So on the left, we see a few of the popular smart smoke detection systems that are available, including Nest, Birdie, and Fibaro. And on the right, we see the few big companies that have built pretty good Wi-Fi repeaters. But currently, we have not found any commercialization of both of these products being encapsulated into the same device. So with that in mind, we set out to design our product, and our 10 deliverables that we wanted to achieve with this project include detect smoke, temperature, and carbon monoxide accurately, be able to have a false alarm mode so the user would decide if the smoke would trigger no matter what, or if it would need smoke and temperature as well to trigger to sound the alarm. Our device serves as an access point between the user and the router, acting as a repeater to boost the signal. It has a built-in rechargeable battery, so you'll never have to worry about swapping out the 9-volt like most smoke detectors have these days. We can send real-time email and SMS alerts when a hazard is detected. We have an audio and visual alert system with LEDs and the audible alarm. Backup mode in case of a blackout, so if we lose hardline power, the rechargeable battery takes over, so you don't lose the ability to detect a hazard. And antenna design and fabrication.
So now we'd like to go over the overall block diagram for the entire device. So what you see here is taking in hardline power through 120 AC. There's a 5-volt power supply which powers the Wi-Fi repeater system, as well as the 3.3 output which powers the sensor system based in the PIC-18 processor. There's also a 3.3 volt backup battery. If hardline power is lost, non-essential systems such as the Wi-Fi repeater will turn off. It'll switch to a power saving mode running only the safety features, so the alarm and the audio system, like a regular smoke detector. And as soon as hardline power is restored, then the smart systems will automatically turn themselves back on and begin performing their functions.
And here we have the hazard detection algorithm. And how this works, we have our smoke alarm check, our temperature read, and our carbon monoxide level check all happening simultaneously. And so we have a few different potential hazards, one being where smoke is detected, but there's not a high temperature in a room, and vice versa. So those will not sound an alarm, but we will notify the user. As well as if carbon monoxide is detected, it is designed to work with NFPA standards on when the alarm needs to sound, depending on the concentration of carbon monoxide.
And now we just wanted to show you a quick picture of what this final prototype looked like. We have a 3D printed enclosure, our PCB board here, and then the BeagleBone Black with a Wi-Fi attachment to power the wireless systems.
So next we'd like to cover some of our schematics really quick. This is our initial power supply. It takes an AC power source, which is traditionally available in most newer smoke detection systems. And essentially what we wanted to do is make this flawlessly, very easily plug and play type of deal, so you don't have to install a bunch of other hardware or systems to incorporate the system. So we also incorporated tons of filtering because we are using Wi-Fi and using our device to transmit and receive. We also, this is the power supply for we have a backup battery. This goes into a 3-volt regulator to ensure that we have stable levels because we are doing so much sensing. And we also incorporated a voltage boost converter for prototyping, just that will eventually be gone. This goes into our sensor system. This is our smoke sensor circuitry and our CO circuitry. This is our main sensor systems controller. It's a microcontroller. It's a PIC18F from Microchip. We added some headers on for prototyping and in case of problems or relevant issues. This goes into our alarm driving circuit. We have 2 different alarms. We have a NFPA 3-pulse alarm for smoke, and then we also incorporate a 4-pulse CO alarm. And then lastly, this is going over our design. This is the layout for our board. It was a 2-layer board, features tons of SMA surface mount components. We wanted to make this minimal and very small size, but unfortunately some of the size got boosted up because it was a prototype board, so we did involve a lot of jumpers and prototyping practices, and then this is the end board fabricated. So
we're going to start talking about how we actually went about testing the system to make sure it works. So since I covered more of the hardware detection, smoke detection system, it all started on a breadboard. So this was our first, I guess you could say, prototype on a breadboard, where we were able to test. On the left we see the circuitry for the smoke alarm. On the right we see the CO alarm, and in the middle we have the microprocessor, and that little guy is our infrared temperature sensor. So the first thing I got working was the temperature sensor. It was kind of difficult to work with. It uses a protocol called SM bus, which is similar to I2C. So it's a digital sensor, so it's really picky. And it took a while to get that working. Up top we have a screenshot of the actual communication protocol. And below I used a serial to my PC to be able to determine if the temperature is reading correctly. So that's what this is showing down here. And I was actually comparing these values to a store-bought infrared temperature gun, and almost every time it read within a degree or 2. So I was able to determine that the sensor is reading the temperature accurately. From there, after testing all the different systems, we did final testing of our whole prototype in a fume hood. So we actually used real smoke to detect, to make sure that the carbon monoxide and smoke alarms both functioned. On the left we see there's a little ball of paper on fire down here. So we're getting smoke to the smoke chamber, and you can see the red alarm has been triggered, which shows smoke. And on the right, the green LEDs represent a carbon monoxide. We have a video for that, and if we have time at the end, we can show a live demo of that.
I work mainly with the wireless capabilities, the Wi-Fi repeating, as well as the smart home tech, which is the smart alert system, logging, and information that is relayed back to the user that's taken from the sensor system. The system's based in a BeagleBone Black with a W1835 Wi-Fi chip on top. And basically, all the power is really contained in this top white, the cape. It powers all the Wi-Fi systems, handles all the 802.11 protocols, is capable of, it functions as 2 WLAN devices. One WLAN device connects to the home router. That's pre-configured, so as soon as the system boots up, it'll look for the pre-configured router that it's set to work with. It'll connect to the router. Then a second WLAN device will be created and managed. That will be set to work as an access point, and that will lease IP addresses to nearby devices. And then a software bridge IP forward creates a connection between those two, so any client that's connected to our device is then passed used as a proxy or signal boosting proxy, and that's how the Wi-Fi repeater system works. So I did some testing, quality of service, and what I found is that the device is capable of handling the throughput. We lost no speed when testing the throughput. What we did find is there's an increase in latency, which is not unexpected because you're passing the information through a whole nother device. But even then, it's very, very manageable. When you're browsing, you won't even notice it, and even on streaming video, there's little to no lag on standard testing. And we also have the RSSI of the signal noted here, and what we're trying to show is that when the home router is far away, we'll even get higher data rates. So you'll see we have 4.49 down here and 3 here, because there's a lot of packet loss with this negative 70 dBm router, and through the boosted signal through our device, we can even achieve higher speeds than we would connecting to the regular home router. Up next, I have an example of what an email alert looks like. So as soon as a particular alarm is triggered, it'll be passed to the smart alert system, which will generate an email based upon exactly what triggers it senses. So it'll let you know automated alert, smoke alarm triggered, what the temperature of the room is, what the smoke alarm status is, and what the carbon monoxide status is. And we also implemented SMS alerts, and those are a little more simple as they have to stay within 140 characters, but they still give you all the pertinent information so that the user can respond accordingly to any alarm trigger. And here's a testing photo of what happens similar to the throughput testing. You can see that we're connecting, this wired router is the SSU network. So what we did is we connected our device to this router, and at 70 feet away now from the regular router, where we'd normally be receiving negative 76 dBm, with our device boosting the signal, we're at negative 38.
Just really quickly, some of the testing we did for the power supply was loading it down to ensure that it was compliant and it would sustain life testing. So this involved loading it down with an incredibly small value of resistor and ensuring that none of our components are getting hot. And we did this for about 6 hours to ensure that it was very stable, and it worked totally fine. Next, I'd like to get into RF aspect of our project, a little bit more of the antenna aspect. This is actually a facility at Keysight. It's an anechoic chamber. It's a 5 meters, and they use this to characterize RF components of their devices and so on. And we actually got the opportunity to go up there and begin their first antenna characterization tests in the chambers, which was really nice, and we'll get that in a little bit. So what was important about our antenna was usually with patch antennas, they're really great because of low profile, but they're fairly directional. And then the other hand is the really good thing about whip antennas is that they have a really good propagation pattern, but they usually stick out. And so we wanted to keep this a minimal form factor device. And so what we needed to do is develop something that was flat in very small form factor and capable of being tucked into our package. And so how we did this, we developed a flat omnidirectional patch antenna, which is it's a very, very revolutionary design. There's not a lot of research on it yet, so we're dealing with that. But we actually created a prototype that works phenomenally. So we'll get to that in a little bit. Before I get into that, we wanted to look at Freeze equation with our system to characterize it. This shows a power curve. If this is 0, you would get your optimal power. And as you go further and further away in meters, you can see that roughly with most Wi-Fi systems, they usually taper out about negative 70 dB, which is this level right here. And that ends up being around 50 to 60 meters away. So that would be the optimal range for our system. And so keeping that in mind, we implemented this with a traditional Wi-Fi router system, Cisco characteristics. And then we implemented our device to see how far it would go under calculations. And theoretically, we would be actually extending your range for your Wi-Fi system up to 160 meters, which is very significant. Going back to the antenna, this is the radiation pattern for our antenna. This is a simulation done in CST. It's a program for characterizing propagation patterns and return loss, S11s, all these different aspects of antenna design. And these diagrams display, red would be the area of most gain or propagations, most powerful. And if the antenna is oriented flat, this means that it has a very omnidirectional, outward, expansive radiation pattern. So you can orient this. You don't have to worry about what rotation it's at on the ceiling. So you just basically install it, and it gets a very, very wide area. These are some of the iterative process that it took to make this antenna. Unfortunately, there was a huge mismatch between simulation and actual prototype. So it took a lot of antennas to finally get that prototype, but we ended up getting it. And these antennas take roughly about an hour to make, so it was incredibly frustrating. But in the end, we came out with a really great design. And we took it to Keysight and characterized it and used it using their industry-grade equipment, full line, like top-of-the-line stuff. And what we found, these are actually the graphs we took. So as you can see from this one, this would be as if the antenna that you're measuring with is pointed in planar with it. And you get this donut-shaped radiation pattern, which means that it is, in fact, going outward. And so this was really an astonishing result, because this proves the concept is actually working, and it's working exactly as planned. This one, however, the result kind of got this very, very deep, low signal region, and we believe that was because of the connector was actually on the measurement. It was oriented directly at this angle, and so we may have gotten some shielding from that, but for the rest of it, it is a very outward propagation. So this is actually us last night at the. You want to explain this?
Yeah. So this is the happiest moment. This was the 5 p.m. circuit scenario where at the science symposium we had everything fully functional packaged into it, and the smiles went away for a little bit, but they're back. So. Do you want to go to the demo? I think we probably should.
Yeah.
So maybe we should.
We can just
Yeah.
go through. Yeah.
So we have these things that are pertinent to project, but we'd like to show you the demo without taking too much more time. But first, we'd like to have some acknowledgments. We'd like to thank Dr. Haider Khalil for being our advisor on this project. And we have a lot of amazing people who supported us and helped us get to where we are, and we're really pleased with how it turned out. So we have these people to thank for helping us.
Yeah, and we also like to thank our industry client, is Ted Boda. He's been in the smart home industry for quite a while, and he really helped us. He really gave us some really valuable input, which helped us work with our product more and develop it into what it is now. And also, we'd just like to finish it by showing our webpage that it's up and functional, and the link is in the first page as well as in our documentation.
So while we're setting up the demo, we'd love to field some questions if people.
Yeah, the question I have is, could you explain a little bit about how the three of you worked together as a team during the project and what you learned from that?
Yeah.
Right. So the biggest thing that we found ended up working fantastically for us is we all have absolutely complete different skill sets and interests, and we were able to take those, combine them to create something really greater than the sum of our individual knowledge, because to build a device like we have here, you need software experience, you need a lot of hardware experience, you need experience with embedded systems. And since we were able to bring that all together, we ended up, I mean, we were told that we'd hate each other by the end, at the beginning, but that didn't really seem to happen.
Only a little bit.
Yeah, you know, there were some frustrating moments, but it worked great.
Success has a way to bring people together.
Yeah.
Exactly.
Do you guys have any industry interest in your product at all? Like any outside sources that have come to you and been interested in investing? Or?
Currently working on that. We would love to move forward with this, but due to like things such as like patent stuff and legal issues, we kind of need to devote more time to developing that aspect of it. But yeah, certainly. Huh?
Are you pursuing a patent?
Eventually, yeah. Would like to.
Yep.
Yeah, let's say that the receiver is sort of equidistance between the router, wireless router, and then the repeater. And the signal is basically the same. Maybe one could have some nanoseconds of delay. How would the receiver handle this thing? I mean, it's like a collision right now.
So part of the configuration of the device itself in the Wi-Fi system is an automatic channel selection. So it calculates the power of the 12 different Wi-Fi channels, and will choose the one with the least amount of crosstalk. So unless you have 12 routers or repeaters in the same general vicinity, with the automatic channel selection, you really wouldn't run into the problem of.
But you didn't have any problem, right? I mean, you did not experience any of such problem, did you? For, let's say, the power being the same, exactly the same from both sources.
Oh, so I mean, if the idea is that the router is placed, or the repeater is placed about halfway between the distance of where you are and the router. So you could run into that problem, but the way the device is right now, it acts as a completely separate network. So it's not, you wouldn't have the problem of two mixed signals on one network, because the repeater operates as its own separate network. So if you're connected to the device, you're connected to the device. And if you're connected to the router, then you'll be connected to the router. So you, if the project were to change to try to have one network and you just switching between nodes, such as the SSU secure network, where wherever you go, you will automatically connect to the most powerful node, then you'd have to start dealing with that problem. But the way it stands now, that's not a factor.
In the back left.
Yeah, since this takes 110 volts, I can see it being used maybe in a retrofit situation where they've already got 110 alarm system in the building, or a new construction, certainly. But do you have any feeling for the percentage of alarmed buildings, say in the United States, that are either just use the battery-powered ones versus 110?
Yeah, as far as we're concerned, that I mean, yes, there are a huge number of devices that require that don't have the built-in 110 AC. However, I think through our research, we found that most new systems actually require the 120 volts. So for future buildings and stuff, this would be like the most optimally like intended for that type of situation. But yeah, unfortunately, the system is too power hungry to drive itself off of a battery itself. But yeah.
Yeah, there's an actual new regulation that went into effect last year. I'm not sure if it's all California or just the area, but it actually requires that smoke detectors need to be hardwired now. So if within the next 5 years, we'll see more and more houses that require the wall power.
Is it feasible to imagine controlling the signal not to go beyond a certain limit?
So,
and let's say you have a nosy neighbor and you don't want
right.
to go there. What do you
Secured.
That's actually one thing that would have been great for us to mention, is that the idea is, since you have multiple of these repeater nodes, you can actually reduce the power of their output. So part of the configuration that the wireless device allows is the power output of the Wi-Fi system. So completely changeable. If you only want it to operate within a room, you can just turn the power down to until it only covers the room. I mean, obviously you'd have to do some testing to figure out where exactly you begin to lose signal, but if you can find that out, then it's as simple as changing a configuration.
But not the shape of the signal, the lobe of the signal. That one you have to put a different antenna.
We could add some, we could make it. It would take some time.
It would,
lots of
a
simulating.
different antenna would, I guess, would.
Yeah, but yeah, I mean, we could try to do something like that. Maybe a patch antenna that orients itself or something.
Should we get that going?
Yeah. Casey, did you have a...
Yeah, you mentioned it in your presentation, but I just want to congratulate you on the radiation pattern you're able to achieve with that antenna design. It's a really unexpected result because the patch antenna radiates directly upwards, and you were able to achieve an omnidirectional pattern with that. So
Yeah, it's really, really bizarre science going on. It's actually called the zeroth order resonator antenna, and by matching the capacitance and impedance of the planar patch antenna, you achieve this, like it basically goes from a direct lobe, and then as you tune it, it just pops into this omnidirectional zone. So it's really incredible.
that's pretty remarkable. And also, my other question is, how did you manage to get the smoke back into all those components?
In the test? In the test? Is that what you're talking about?
No, the power blow.
Lots of coffee. Yeah, it was an interesting night.
All right, so
We'll get this
I guess
set up.
we'll.
Incidentally, how much did it cost? I mean, I couldn't forget.
Yeah,
Right.
we had finances, but
The overall cost of everything, if you were to make another one of these tomorrow, would be roughly $246.
$245 was about what it came out to. Mm-hmm.
So
And
with everything, and that's buying at minimum quantity. Like if you're buying just enough resistors and capacitors, we actually did the analysis on the cost. If you were to buy in quantity, say for example, 1,000 parts of every component, and it actually drops the price down to $70. So there's a huge, huge markup in buying very minimal quantity. So it would be a realistic marketable product, but not in this, like not with minimal quantity. So.
Should we get this
All right.
running?
So,
So
Should we get it set up more?
you also, as part of your network, do you have any encryption at this point, or?
so the design process I took was get core functionalities working, and then go back for additional, and that was one of the first things I went back to after getting the Wi-Fi repeater system. Security is obviously incredibly important. Ended up implementing WPA2 encryption, which is the standard recommended encryption method for Wi-Fi networks as of right now. So it's up to security standards.
So you have the demo?
Yes.
Yes.
So.
Waiting for it to boot up.
So what happens is once power is applied, the device will boot up. I spent a lot of time making sure everything was automated. So now all of my scripts are put into the boot queue of the system. So as soon as power is applied, all the systems will begin running. So as of right now, if you were to pull out your smartphone or your laptop, you should see a network called Wired, which is this device acting as an access point. For the demo, because we didn't want to just kill the throughput by having 50 people log on at once. I've set the number of IP leases that the device can give out to 1, so you won't be able to connect, but the network will be there.
And it's connected, there's a router plugged in back there, which is what it's repeating through right now.
And then so one demo we'll do is we'll just trigger an alert, and then I'll
should we maybe close the door just for a couple minutes? It's
Yeah,
kind of loud. We don't want to freak anyone out
audio
studying.
alarm.
So we have these little smoke test, basically sprays out fake smoke. So we'll test the smoke sensor first. And just by doing a couple sprays. That actually triggered it.
All smoke's going on now.
Yeah, there it goes. So this chemical actually triggers the smoke alarm as well, or the carbon monoxide alarm. So it'll sound until it either gets silenced, or if you kind of give it some air, the smoke will clear out and it'll turn off on its own.
Does it have a silence override button?
There, yeah, we do have two silencing buttons,
night, so
but that was
it was a
casualties. So since it did detect, and then so now the smoke alarm or the carbon monoxide alarm will not go off again.
And let's see here. I already set myself as oops. Oh, no, there it is. Okay, so, yep, and there we go. That's the alert coming in. So this is an automated message. The smoke alarm was triggered and high temperature detected. The temperature detected is 84 degrees Fahrenheit, and there was a high level of carbon monoxide detected because we set off the carbon monoxide alarm with our smoke. So that's the basic demo. There's a lot of features to the system we love to show you, but in the spirit of trying to not blow ourselves up, we might hold off until we can do some more testing on exactly how thorough the repairs to the system were.
Okay, so this is our project. It is called Laundry Now. My name is Ryan Russell.
I'm Frank Bonforti. And then our advisor is Fried Fairmont, and our client is Tremaine Austin Dillon, who is a Res Life coordinator here at SSU in the Sauvignon Village. So quick overview of the project itself. We're going to go over problem statement, product comparison, our 10 deliverables, system block diagram, final product, our schematics, our testing that we've done, the challenges we've run into, future work, the numerous presentations we've done, and then supporting classes, and finally acknowledgments. So to start off with, the problem that we're originally addressing is pretty much a problem that is something that occurs here either on campus in the dorms or in apartment complexes that don't already have a laundry monitoring system. Currently in the state of California, there's roughly 6 million residents that are in apartment complexes. And pretty much what we wanted to do was make a system that would allow clients to be able to determine if a machine is running or not from basically the comfort of their home, and then be able to do their laundry accordingly.
So from the initial idea of the project, these were our simplified goals list. We wanted it to be expandable based on the number of machines, so it wouldn't be dependent on how large the laundry room was, that sort of thing. We wanted it to be non-invasive. We didn't want to have people replacing entire machines, and inexpensive to purchase and install. Again, that kind of goes with the simplicity of it. Simple to use and reliable. We didn't want a lot of issues. There's upkeep to the system. The system is designed partially to help reduce the amount of maintenance that is needed, and so maintenance of the system kind of defeats the purpose of it. And we wanted to be able to track machine usage. To go next.
So some similar products to what compared to Laundry Now is the first project is called Laundry View. It's actually the main competitor to our product. This product is a online and app now generated viewable system that allows users to view their the machine usage, the times they're left on the machines, the doors opening and closing, what's available, what's not available, all that sort of information. You can view it online, which is this Laundry View program. This program does require the use of purchasing brand new washers and dryers. So roughly a washer and dryer costs around $1,500. So when you start replacing all the ones in, say, a laundry facility, it adds up pretty quickly. The other one is this remote laundry monitoring system. It's not really a system that you'd use commercially. It's more of a system you use at home. Basically what it is you have a modem that you have to physically install in the machine, which then communicates over the power lines to a handheld unit, which you have to plug into the wall basically what the time left is on the machine and when the machine stops. So those are pretty much the two main competitors. Otherwise, there's nothing really else.
So our official list of the 10 deliverables, this is what we intended to accomplish, this is what we accomplished for the project. Snap together sensor design, allowing for easy configuration and node replacement. You can see this right here, and we'll talk about this a little bit more in the demo. Everything snaps together. It's very simple, it's very easy to use, very easy to install. Able to determine if a washing machine or dryer is in operation or stopped. That is kind of the main goal of the whole project, is to be able to view this online. SD card saves and backs up usage data when there's a lack of power. This is more for maintenance. The facilities management and the maintenance teams can look at the web page and see which machines are being used. But if the power goes out, it saves that data to an SD card. So when the system does come back up, that information is still there. The website displays the status of every machine and updates every 5 minutes. It doesn't update more than that because really it's not necessary. A machine runs for approximately 45 minutes, so a 5-minute update interval is plenty sufficient for it. Ability to access the website from anywhere with internet access and on the local area network. This is doable. The way this system is set up is it connects to your local area network, and you have to be on the same network to be able to access it. Some routers do support a feature called port forwarding, where you can set it up. You can type in your router's IP address, which is assigned by your ISP, Comcast, or whoever, and you can set it up to forward port 80 to the Laundry Now server. So you can be anywhere in the world and access this, or anywhere in the apartment complex and access this. It automatically detects the number of sensors on the machines and the number of machines that are there. When you plug it in and the system initially starts up, it automatically detects what's there and it builds the web page based off of that. Viewable on the website, the number of cycles per machine for day, week, and month. Again, this is more for the maintenance teams. You can track all of this data and it automatically backs it up and everything. Indicates on the website if a machine may need maintenance due to lack of use. This is implemented again for maintenance. If there's been no usage on a machine for the last 7 days, it flags the machine as a possibility for needing maintenance. It'll show it on the website, and we'll show that during the demo, how that works. Non-invasive design sensors can be attached without modifying pre-existing equipment. Again, this is the size of the sensor node. It is fairly large because we use through-hole components, but it's fairly non-invasive, and they stick right on. Continuously tracks sensor data even if the server is not connected to the Wi-Fi. So if the Wi-Fi network goes down for whatever reason, the system is still going to track the data. It's still going to be doing whatever it needs to do, and then when the network comes back up, it can be used as normal.
So basic design that we're going to go over, and then also our demonstration unit, is we have a main server here which directly connects to the LAN network. And then we have off the main server, it connects to 2 controller nodes, which each controller node will basically determine the usage, well, not the usage, the cycling of the machines themselves based off sensor nodes that are connected to the back of the machines. All this is done via serial communication. So you basically you connect them in line and they just all work. That's pretty much the design. Here's our actual product. Here we have the server itself. Then this is one controller node, here's the other controller node, and then these are the sensor nodes here. So it pretty much follows exactly what our demonstration unit is.
Okay, so I'm going to talk briefly about the schematic. A lot of the stuff we did talk about at the midterm review, so I'm going to kind of go through this a little bit quickly. The server has a number of different components. It has a real-time clock to keep track of the current time. This is used for the data tracking, so it knows which cycles go with which day. That's this guy over here, and it is connected to the main PIC32 microcontroller. We're using a 32-bit microchip microcontroller that is acting as the server. It's built onto a board, and we can show a picture of it, that is integrated with the Wi-Fi chip, which is also a microchip connector. This board right here represents the entire server board, which includes the Wi-Fi controller and everything on it. These are the 4 connectors that we have to go to the different controllers. It supports up to 4 controllers, and each controller supports up to 8 devices. So that's a total of 32 machines that the system can handle. Next slide.
Okay, so this is actually the controller node schematic. It's pretty simple. You have your PIC 18 here, which is basically the controller node, the brain behind it. Then this is actually the Ethernet connector that runs to the server itself. There is a switch here which basically allows you to toggle the operation mode between your washing machines and your dryers. So what this means is each controller is set up individually for either washers or dryers, and every sensor node connected on that line has to be for washers or dryers. In every apartment complex I've seen so far, they always keep the washers on one line and then the dryers on the other, so this really isn't an issue. Then this right here is actually a non-inverting Smith trigger, which basically acts as our buffer, cleans up the SPI signal coming from the sensor node, which then goes out through another Ethernet cable. As for the sensor node, they're pretty much designed so that all communication flows basically in one Ethernet port and right out the other. It does go through the buffer at the time, so it's going to clean up the signal. So basically what it allows us to do is that we can have up to 10 feet of wire in between each sensor node or the sensor node and the controller node with the with these buffers added. Then what it does is it goes into, this is our demultiplexing chip, which basically takes 3 lines in and then basically pushes 8 out, which then goes into a switch here, which basically allows the user to manually set the identification number for each machine. It basically allows us to have the same sensor node on every machine, and then all you have to do is change a switch. So it's pretty universal that way. As for testing, we did quite a bit of testing. We did bench testing in the lab, and then we also did testing on site as well. So we did sensor communication testing, pretty much making certain we can communicate with the sensors, which this at first was actually rather buggy. Then we did serial communication over distance. We wanted to make certain that we could get 10 feet of distance from the controller node to a sensor, and then from a sensor to another sensor. We basically wanted to make certain we have the distance, which this is where we actually determined we needed the buffers. Then we did parallel communication over distance, which is the server to the controller node. For this, we're actually using USART, not SPI, so it's going slower. So we don't actually need to buffer the signal going in. The chips themselves will be able to determine themselves. And then finally, we did Wi-Fi distance. We wanted to just determine what's the range on the Wi-Fi unit on our server node to a router. Then on-site testing, we did best mounting locations. You can learn a lot about a washing machine if you do numerous machine usage. So we determined the best mounting location of the machine. We did best machine configuration, best time delay for the sensor reading. So this is when we're taking signal in, we're actually reading the X, Y, and Z components. We're averaging those, and then we have a delay, and then we do it again. We're basically trying to smooth out the signal, get a more accurate reading. And then we actually do this even more so with averaging. We actually take a signal and average it so it becomes a more smoother line instead of really jagged spikes, essentially.
All right, so this is the board that we primarily tested with. We didn't get the PCBs until later in the project. So this is primarily what we use to do all of our testing, which we're going to go a little bit more in depth to. This is the chip kit board, the digital board with the Wi-Fi controller. The PIC32 is right there. And then we have 2 controllers and a sensor on each controller. And then there's the real-time clock to keep track of the time and the date and everything. So the first one we did was sensor mounting location. We wanted to determine the optimal place for seeing the motion of the machine. We found that the best place was on the back of the machine. It was the most direct, gave us the highest intensity. You can see it right here. We plotted this using MATLAB with an average intensity value of 73.5. And then we tested a couple other ones. We tested it on the side of the machine, and we also tested it on the top. Those 2 locations, not only did they not provide optimal movement transfer, it was also kind of in the way. Having a sensor on top of the machine kind of defeats the purpose of non-invasive. It gets in the way of everything. Next, we wanted to test stacked machines. Could the sensors determine between a machine stacked on top and the machine stacked below? Can it tell the difference? The way the system is set up right now, it cannot tell the difference. The dryer algorithm and the washer algorithm that we use does it based off of some preset values and then some automatically determined values. With two machines operating that close together, the movement is too large between the two. It wouldn't be able to tell the difference. This would be fairly simple. I say simple, but it would take a little bit of time and a little bit of work. But comparing the two graphs together, you can clearly see the difference. And so this is definitely something that in the future could possibly be implemented into the system. Next, we looked at the data points. When we first gathered the data points using the sensor, this is the graph that we got. It's kind of difficult to work with. You can see these really high spikes and these really low spikes. And so what we did was we used an averaging algorithm that just averages a bunch of data points over a set specific time. And we determined the 20 data point was the most reliable. These got a little bit too smooth as we bumped up into the 50, 100, and 200 data point averages. This provided the most consistent and reliable results from what we found.
It also slowed down the actual communication, because while the controller node is talking to this one sensor, it's not actually talking to the other sensors. So by having these higher data points, it's not talking to them. So by having this lower data point, it's allowing it to move faster and it can determine faster. Still though, the time delay on this is less than a second. It's right around, I want to say, maybe 500 milliseconds. So it's actually pretty fast.
And then we also did this for the washing machine. Similar type of thing with the graph. With you looking at the raw data points, you can see there's very high spikes and there's also very low dips on all the data points. And that makes it really, really difficult to determine if it's actually moving or not. It can trigger different parts of the algorithm. So what we did is we averaged it out. Again, on this one, we also used a 20 data point average. It provided the most consistent results. It worked the best with our values. And you can see this, again, at the 50, 100, and 200 data point averages, it gets a little bit too smooth and it doesn't work as well.
So possible problems that we could run into with our system is false triggers. If a machine's too quiet, basically if the people who install the machines do their job really well, we will actually run into issues. The Wi-Fi router not being in range, we did run into an issue where if the router was out of range, it will not connect. Then users not being in range of the Wi-Fi, unable to access the back of the machines, say the machines are more pushed into an alcove and you can't pull the machine out. And then loose connections due to the continuous wear. We haven't done long-term testing yet, so the sensors could essentially shake themselves apart. So it would just require more testing.
All right, so some of the challenges that we faced and some of the changes that we made. Loss of SPI data communication on the PCB. About 3 weeks ago, we got our actual PCBs in. We hooked everything up. The server connected great. The controllers connected just fine. We had no problems. And then we went to test the sensors. Initially, we thought they were working perfect. We were getting numbers. Everything was working great. Unfortunately, the numbers we were getting had no correlation to movement of the machine. It was literally random data, which made it really difficult to determine what was wrong because it was clearly connected and the server and the sensors were responding, but it wasn't anything useful. It took quite a bit of time to figure this out. We spent probably 2.5 weeks on this.
We rewrote the entire controller algorithm, I want to say 3 or 4 times, which was quite enjoyable.
It was difficult. We finally figured out, looking at it on the scope, watching the actual bits going across the scope, that every so often the data return line from the sensors to the controllers was inverting itself. We did do load tests, and we did do distance tests, and we did not see this problem. We think it's partially because of the Ethernet cables, the twisted pair, they may be interfering with each other. That combined with the added load and the distance all together, the sensors just couldn't handle it. We were able to get the last sensor on the line to respond, but none of the others. So we determined that's what was wrong. We added pull-up resistors to the actual sensors themselves, and all of our problems were suddenly fixed. It worked perfect. We decided to add an SD card. Originally, the system did not include an SD card. The system is capable of it. The chip kit board that we're using is capable of it, but we did not intend to use it. But later, we did determine that we wanted to be able to back up data in case of a power outage, and so we did use that. In the original proposal, we wanted to use a system called WPS, Wi-Fi Protected Setup. That is the system where you push the button on your device and you push the button on your router, and they automatically connect. The Wi-Fi chip is capable of this, although we found out later that the digital lint libraries that we're using to do the Wi-Fi communication on the chip itself does not include support for this. So instead of writing our own libraries to do this, we opted to have a program that would ask the user, that you could plug into your computer, ask the user the SSID and the network password. It would be on the SD card, and it would automatically load that from the SD card. Another change that we made in the initial proposal, we had intended to try to determine if the door had been opened and closed to see if the machine was loaded or not. We were able to do this. The initial test before the proposal showed that we were able to do this. The problem that we ran into was error detection. If someone walked up and kicked the machine, then it thought the door was open. So it was kind of a problem. Our workaround for this was to add a just finished status on the web page. And what this does is when the machine goes from running to available, the sensors determine that, and the controllers report that back to the server. The server will display a just finished status to indicate that there is a possibility that there's still stuff in the machine, and also to let people who are watching to see if their clothes are done can look and see that their laundry is completed.
So our future work, what we've basically for all the things we'd like to add to this system, first of all, we'd like to incorporate door detection. This is one thing we'd like to do. With the averaging, what it does is it smooths out all those points, but with the sensors we're using, they do have a double tap, a single tap, basically register in them, which will detect sudden spikes. So we could do door detection. It would just take a lot more testing to do it. Basically, the next thing we want to do is the ability to detect stacked machine movement. So what this would require is taking a comparison between the bottom machine and the top machine, seeing if they're both above a certain threshold, or if one's above and one's below, and basically averaging them out. And it would basically take a lot more testing to figure out. The next thing would be add a work order request page, basically to the website itself, so users could say to property management, hey, this machine's not working, could you work on it? Basically allow users to pre-flag machines. Incorporate graphs to display the usage data. Right now it just displays the numbers. We'd like to be able to display graphs. It would make it a little more visually appealing. We'd like the server to be able to support more networks than just WPA2. That's all it supports right now, so we'd like it to support others.
The chip kit board is actually capable of supporting all of the WPA encryption and all the other types. Since we lost about 2 weeks due to the SPI stuff, we weren't actually able to implement it into our system, but the chip kit board is certainly capable of it.
And then the next thing is we'd like the server to be able to support configurable IP addresses. So basically what we'd like is we'd like the router to actually assign the IP address to the board itself instead of the board saying, I want this number. We'd like that.
Right, yeah, right now the system by default requests a .195 ending IP address on the router itself. We've never run into a problem where it hasn't been assigned that IP address, but it would be nice to have that configurable in the future.
And then finally, the last thing we'd like to implement is actually a pressure sensor for the machine to sit on, so you could actually detect the clothes being physically removed from the machine themselves, so you truly know someone removed their clothes and not just the door was opened and then closed. The presentations we've actually done 3 so far, and then we did actually talk to the 310 class, but we did the SSU Research Symposium on the 15th of April, we did Market Day on the 21st of April, and then last night we did the Science Symposium as well, and then our funding actually came from the Waters Collaborative. Supporting classes that really were beneficial for us for this project were CS 115, Fundamentals of Digital Logic Design. There's actually a lot of digital logic that we actually had to go through for the communication between the controller nodes and the sensor nodes. We were trying to figure out the best means of buffering a signal between the 2 devices. Then advanced programming was extremely helpful for our graphing. Microprocessor is pretty much the main backbone of this project, wireless communication, and then finally networking.
So a few acknowledgements. We would like to thank Dr. Farman, our advisor for the project. Helped us work out quite a few issues and kind of guide us along on the project. Tremaine Austin Dillon was our industry client. He is the RLC for the Sauvignon Village East, I believe is. He kind of worked with us in the beginning, especially on getting down exactly what the system should do and how it should operate.
He also allowed us to do quite a bit of testing on campus as well.
Dr. Khalil for the initial planning stages, ES 492 where we did all the proposal and everything. He was a very big help through that process. We'd like to thank Dr. Kajuri for his help reviewing a lot of our documentation and other works. Sharam, we'd also like to thank as well for support just through everything, all of the equipment and devices, ordering things that we needed.
We would not know what a Smith trigger is without you,
Yeah.
so
yeah.
that helps.
We also had the opportunity to hire a freshman to kind of help us with some of the more simpler tasks, Jeff Boerkating, and we worked with him quite a bit on the testing, and he helped us with writing some of the simpler programs, the program that grabs the network information from the user. He wrote that. And then we're going to do a quick product demo to kind of speed this up, or actually it's ready to go. So this is what the website looks like. This is live. The system is connected to the router that is sitting down over here. As you can see, there is 2 controllers and 2 sensors connected. So this could represent a bank of washers, and then this could represent a bank of dryers. Each has 2 sensors on it. This, the exclamation mark here represents the usage not happening over the last 7 days. That's kind of the error detection mode. Refresh. So I've just been shaking this sensor. It is now activated as running. Right now we have kind of a special demo code that is loaded onto this. Normal operation would filter out small movements like this. But since we're here to demonstrate the whole system working, we have modified it slightly to include that so that it will work. So I'll set this sensor down.
Normally, without the demo code, we would be shaking the sensor for 5 minutes. So
yeah,
in order to speed things up, we made a demo code.
Take quite some time. This is the just finished status that displays as it's finished. This would normally be a 5-minute interval that this would stay up here, but since we've accelerated the process, it's going to display it for only a few seconds. And down here, before this said 37, now it says 38 because the machine has indicated that it's completed and it has incremented itself. This data is backed up to the SD card right now. Obviously it loaded when I turned it on just before the presentation. It loaded this data back up. And then at midnight every night, the real-time clock sends a signal to the microcontroller and it shifts all the data by 1 day. So if it was midnight, this would all shift over. And then the time it's timed out, so now it's back to a finished status.
If it comes back.
There you go. And so, just hit.
I'm looking for it. There we go.
So any questions or comments? Yes.
Yeah. I have 2 questions. First of all, does your machine, your system, monitor the number of minutes or whatever that the system is in use, or remains to finish?
It doesn't on the server itself. It does on the controller nodes. It does keep track to see if, because the washing machines, what happens is for the washing machines, you'll have a period of movement, which basically is right around 4 to 5 minutes. Then it goes into a just soak cycle, which it doesn't move for 7 minutes. If it doesn't move again after right around, I think, 12 minutes, then it'll actually go back and say it was a false read. It's actually available.
Yeah. I recommend that you include this in your future work because the user really wants to know how long, this machine, he needs to wait for this machine to be available. I think this is a very good thing. The second question that I have is that for the humidity, let's say that, in an environment where there's a lot of water and so on around the washing machine and so on, you may need to include, I can read it in your write-up, something about that this needs to be probably enclosed in a waterproof type of thing and so on. Yeah.
Didn't think of that.
Yeah.
Very good.
I had a question regarding how the data gets to the web server. Like, what sort of communication between yourself, between the controller nodes and the web servers happens?
Yeah, so the data that's transmitted from the controller to the server is sent over UART, and it actually sends a register, an 8-bit register, and each bit represents a different machine, and so it sends that over, and the server is able to decode that and determine which machines are running and which machines are not. And then as the server reads that, it saves that into its memory and backs that up onto the SD card.
We actually develop our own handshake for the communication in between the server and the controller node. As for the controller to the sensor node, there's no handshake. It's purely give me what information you have, and then it sends it back. That's pretty much how it works.
Yeah.
You said that your system ignores small vibrations like what your hand just did, but I mean, for the presentation that was changed. How noisy do the washers and dryers have to be for this to work?
What we found is at my apartment complex, we actually have extremely well-balanced machines. So what we were finding is like the average we were getting was right around 20 for it to actually trigger on. So when you're moving, like these sensors aren't moving very much. It's very slight movement. So it's 20 out of the scale that's 10-bit register essentially. So it's only going the 20. So it's really slight at the end of the day. I guess that's it.
Okay, thank you.
So hello everyone. Our project is the weather satellite receiver. I'm Alyssa.
I'm Joe.
And I'm Alberto.
Our advisor was Dr. Haider Khalil. So one of the main key selling points of having this is that it is good for raising awareness of weather and environmental issues, because this receiver will be picking up APT, which is automatic transmission pictures, ATP, of the Earth as it circles around the globe. And so we can use this to see weather patterns, and then it can be augmented to receive other satellite images. So there are uses in the fields of geology, perhaps physics, or environmental science studies. And this will be a base station at this campus, which other future students can work on it and improve it and learn from it.
It's also a great learning experience because it involves a lot of circuits and radio frequency stuff and software, and it's also a great tool for this in particular is an FM narrowband receiver, but it will be great also for AM and any other additions that could be done in the future.
So these are a couple of receivers that are currently out right now. The first two, they obviously don't have the LCD display, so it's user-friendly. They also are only on 137 megahertz, and our receiver supports FM radio stations as well. The last one here is the most similar to our product. However, again, it is only limited to the 137 megahertz as well.
Yeah.
Okay, so among our features, we're including the use of a rotary encoder, because the user interface will be all on the LCD screen and push buttons, and then we will also have manual squelch, which controls the noise input, and the volume control. And then on the menu, there'll be several different options. SAT is for receiving the satellite transmission at 137.5, which is our center frequency of our antenna. And then NWR is NOAA weather radio, which is actually the radio transmission from different hazard sites. And then FM is just standard commercial FM, and VFO is variable frequency oscillator. So beyond those three initial options, they are able to, within the range of our radio, choose a specific frequency. And then additionally, we are also including a signal strength indicator and the scanning mode. So it will use the signal strength to actually search for a good channel. And it will be audio, but we also have the feature to plug into your computer so the computer can decode.
So this is our main high-level diagram. It's basically a super heterodyne receiver with dual conversion. Pretty much 99% of all receivers in the world use this same topology. This particular one has dual conversion. Here's the first intermediate frequency, and here's the second. Letters came out a little small, but this is our preamplifier, your antenna, the preamplifier, which will particularly amplify the signals for the satellite. We're not using it for the other modes. Here's our first intermediate frequency and our mixer. What's so special about our radio is that it uses a programmable oscillator. This oscillator has its own crystal control master oscillator and internal PLLs, and it can be controlled through a microcontroller using a I2C bus. And it has a very wide range. It goes from 8 kilohertz to 160 megahertz. So pretty much our radio can receive in any of those frequencies in that range. And that's great because that's what made us expand the radio into having extra modes that otherwise it wouldn't be possible. The other radios we saw previously, they only have 3 or 4 channels at the most, and our radio will do multiple frequencies at any time. And like I said, this is a dual conversion. We are using 10.7 megahertz for the first IF, intermediate frequency, and 455 kilohertz for the second one with a narrow band filter, because that's the type of transmission that the satellite uses. And finally, we'll go through a buffer and audio amplifier so we can monitor the signal and process the image with a PC.
So we'll start going through our schematics now. The first one we have here is the preamp. So we'll have your signal coming here from your antenna, RF signal here. This is a tuning circuit here, tuned to 137 megahertz, our desired frequency. Here's an RF choke, basically only lets the DC through, blocks AC, since this is our power system up here. This will power the transistor here, which is responsible for amplifying. And then here we just have our bandpass filters to let the desired frequency go through.
And this is the microcontroller layout and user interface. The S meter will be one input, and then we have here is the rotary encoder and the push button that comes with the encoder, so that it may select options with the encoder and then actually choose it with the push button. And then we're including a second push button that is separate for resetting back to the main menu. And we just have the LCD, and you can control the contrast with a dial.
And this is again the main circuit of the radio. It's using a Motorola integrated circuit. It's a second generation. We were going to use originally a single conversion circuit, but we found this other circuit that is much better. It's a second generation, and it has the dual conversion all complete in one chip. It also has it has 2 mixers. It also has a limiter and an extra op-amp, internal op-amp that we can use to set our levels for the signal strength. Basically, all the surrounding components are basically decoupling capacitors that have to be placed around the IC. This was done following the Motorola application notes to make sure that we didn't have any problems with oscillations or noise. And then it has 2 filters. One for the first IF, which is 10.7 megahertz, and a second filter, which is 455 kilohertz, which is very popular in AM receivers as well. And this filter does most of the job. It's a 30 kilohertz bandwidth, which is what the satellite images ask for. Here's our demodulator coil that takes care of demodulating the FM into audio. And then all this circuit down here is basically a buffer op-amp. The first section amplifies the signal a little bit to power an additional power amp, so we can hear and monitor the signal as we're receiving the images. And then a second part of the op-amp, which is applied directly to the PC. And it also has a low-pass filter here to reject all extra noise and high frequency, so only the satellite sound will go through. And the rest are just different potentiometers to set a threshold level for the signal strength indicator and so on. Yeah. Testing, well, we did a lot of testing. Basically everything worked from the beginning, both on the breadboard and on the PCB and the final product. Here you can see just a simple image of the spectrum analyzer and the local oscillator. Unfortunately, we don't have a video of this, but if what is nice to see here is that if we, as we tune the radio, this notch will go left and right, indicating that the frequency is actually changing. This is the output of the local oscillator, which is a very clean sine wave. And this is the output of our preamplifier, the 137 megahertz preamplifier. It has a little more noise, but the signal gets amplified when it goes through it. Maybe next one. That's your
Okay.
testing.
So a major part of our project is this antenna, and this is called a quadrifilar helical antenna, and it is quite big because as your frequency is small, the size, the dimensions of your antenna have to increase. And so we built this, and these are the S11 parameters from the actual antenna, and then I managed to model it on FreeCAD, which is a great software for building structures, and then you can port it to other simulation technologies. CAD stands for Computer Assisted Design, and then CST produced this radiation pattern. And so this is looking down on top from here, and so at the very top you get a gain of over 4 dBi, and still pretty strong all around the sides, up to 1 here. And our simulated S11 is slightly off because the dimensions were used from a special calculator rather than the actual mathematical calculations. So it is actually still within our range because 137.5 is our center frequency, and we expected -9 S11.
Yeah, so in our simulation results, we actually got minus 8.4, so we were about 1 dB off. But real-time results were definitely comparable to the simulation results.
For those who are wondering, S11 is just the reflected voltage of the input port. Okay.
So this is the final design of the antenna, as well as the receiver. As you can see here, we have the antenna connected to our receiver here. This was the final board schematics, or final printed circuit board of our design. And then this was the outside of the LCD with the rotary encoders, squelch, and volume control as well.
Yeah, the receiver board required a ground plane on the top using little islands to avoid touching other components. And it's a double-sided board, and that is the main board that hosts the entire receiver. And there's also an additional board in the front, which hosts the local oscillator, LCD, and rotary encoder for the front panel.
So design challenges. Personally, I didn't take the antenna class last semester, so I had a lot of trouble with the 3D modeling software, CST. So it took a couple weeks, a lot of YouTube videos going through that. So I would say that was definitely a challenge.
I would say that applies to me as well. As part of the software, it's a bit of trial and error unless you really know everything what you're doing. And then another big challenge for our radio was tuning the special coils because they had a very small area of accepting our frequency through.
Yeah, for me, I'm a big fan of receivers, and I have an amateur radio license. But I never got to build any receiver of any kind, besides a tuned radio frequency for AM. And this circuit, being a super heterodyne, dual conversion, and all the programmability that it has, it's been a great learning tool from many aspects. As well, the PCB was also a major task. I've never done a double-sided board with a ground plane on top for RF, so it was quite an experience to get it running. Yeah. Also, one more thing. Since we all took that class, the communications class, I always had trouble understanding what happens when you multiply two signs and all those extra values that you get, and everything comes clear once you play with this radio for a little bit. Yeah.
Okay, so as we stated with some of the uses that are potential with our project, some future work would to be exploring what other options we can include in our project. Like I said, with the wide use in SSU study fields, there could be all sorts of satellites and CubeSats, which are very small ones, for monitoring different data at different elevations. And so this could be edited in many ways to receive that.
This could also be computer controlled for more user-friendly features. We could essentially upload these images to a server so people can access this in real time. And then also, I don't know if you guys are aware, there's a ground station system on top of the student center. That's like a couple $1,000s ground system station. So essentially, that one's particularly for CubeSat operation, but essentially they could find use in our receiver as well.
All right, so we presented at the Science Symposium last week, and this project was actually funded by the three of us, in part largely, but it was actually very cost effective. It only cost about $80 to construct the whole thing, and our advisor, Dr. Haider Khalil, said that he actually has certain project grants that he may be able to reimburse us with towards the end.
This will also be available in the EE department forever, so if you guys would like to check it out, or future students, they could definitely use this.
And it's definitely a better receiver than the ones that we saw at the beginning. It's more than half the price, and it has many, many more features than the commercial units that don't even have an LCD to display the frequency or anything like that.
And then this is our webpage, www.wsr2015.wordpress.com. It's fully updated. We have our current slides there, our final proposal as well, Science Symposium stuff, and then all our final project pictures as well, if you guys would like to check that out.
Any addition?
Okay, and then we would like to say thank you for Khalil. He was not able to meet with us as often, but we still learned a good amount from him and received many useful tips. And then our industry mentor was Brooks Hanley from Keysight. We'd like to thank him too. Here are references, and then we would like to give a demo on our video.
Yeah, unfortunately there's not enough reception inside this room, so we made a video just in case, but we're gonna try to test it here as well. So if the video is not working, we'll just go ahead and plug it in. Oops.
Can you play that?
Okay, there you go.
Can you play it from the file?
A big problem we ran with is that the satellite is circling the Earth. It's called polar orbit because it goes through the through the poles, and it takes about 110 minutes to circle the Earth, but only it's only within range twice a day. So it's problematic to be out there at the exact right time. You only get about a 10-minute window of time to basically chase the satellite until the sound is gone, and that's one of the major constraints.
It's not showing up there.
It's there.
It's just not.
We'll just plug it in.
Drag it over to the other window. Try dragging it to both sides to see if it produces.
Try the other side. Oh, yeah,
I can't see it now.
try just putting the mouse over the screen.
Yeah, it was a nice video with all the features. We went through all the features, but we'll just plug it in and.
Wait,
we got it.
Got it.
I don't know if there will be sound.
Now I can't. Oh, there we go. Now there's no sound.
Yeah, keep playing.
Yeah.
Where's your headphones? Your output for audio?
Try it.
Okay.
Turn it up on your computer.
No, it's not. It's not loud, and it's very hard to see.
Yeah, the screen.
Yeah, the screen was in very low light, and it's hard to see. We'll just plug it in.
Okay.
So obviously we cannot test the satellite portion of it, but I don't know if you can see, but it has a menu that you can select with this rotary encoder, and we're just gonna go ahead and use FM radio. But it seems that there's no reception here at all. Yep, I guess the building is. We never tested in this room, and I guess the building is blocking the signal.
The video, it was working right in 2007, just a couple hours ago in the video.
But yeah, it's basically a radio where you get a signal indication, your frequency, and then you have a menu that you can go back and forth to select different options, and it will also allow you to scan. If you press the scan button, it will start cycling through all the frequencies, and if there's any signal that is above 20% of strength, it will lock into it. It will be considered as a strong signal, and that's basically what we can show here. And I think we're concluded. Any questions?
Yeah, in the diagram that we had, I saw the output going to the speaker, analog output. It will be good if you add to your future work the interface with the computer. I mean, so that people can see it on the computer. Because these days everybody wants just to look at the computer.
Okay.
Yeah, it will be basically a small jack output that will take the audio to the computer.
And well, it should be digitized and so forth. I mean, and I did see it. Yeah.
Yeah, especially if we implement software-defined radios.
Did you attempt to optimize the signal reception with different shapes of and sizes of the antenna?
Well, they did.
Actually, this was the only one we've constructed, but the simulation errors were building up in the past few weeks with trying to test it, and then we were considering a patch antenna as well. That's where it's a microstrip of copper layer, and considering 137.5 megahertz, that would be almost over half of a meter of a patch in
Yes,
both
very big.
directions.
Very big.
So we simulated a few patches and we actually got material, but we actually didn't get enough material because it's like huge.
It's
So
a huge
we thought it'd
antenna.
be non-ideal.
Yeah.
to
And most
make it.
people recommend this type of antenna for satellite reception because of the
Coverage.
mushroom type of
Yeah.
shape that covers the whole sky.
You get considerable more gain from a patch, but with the size, it defeats the purpose, I suppose.
Thank you.
Casey?
What's the polarization of the signal from the satellite, and is that the same polarization as your antenna?
The antenna is circularly polarized, so it will take from any angle.
Is the signal from the satellite?
Yeah,
Yeah,
it
yeah.
is as well. Yeah.
Yeah, apparently the satellite, it can be spinned in any position. In fact, when we did testing with a handheld transceiver, we had to move around to kind of align with the satellite at any given time. Yeah.
And this is left-hand circled, and it's actually the opposite from the antenna, so it will receive.
So that antenna has like a big enough bandwidth to do like FM all the way up?
Yes and
It
no.
actually achieves,
FM, commercial FM is so strong locally that pretty much any piece of wire will pick up the energy. Yeah.
Yeah.
But it's specifically for the satellite portion of it. Yeah.
And NWR goes into the 160 megahertz range for the radio.
Yeah, which is like the way.
Did you have a chance to make some experiments with the antenna in an environment which there's lots of moisture and humidity?
Not really. We tried outside in the grass field in front of the building, but no, we didn't notice any
Can you
special.
guess what sort of performance you will get out of this antenna in a
In real environment, not really.
because that's part of
Right. Saying that it's useful.
Yeah.
Yeah. The main problem that we had is that we forgot to add the intermediate frequency to the satellite receiver. So for many days we were trying it without an intermediate frequency, so we were not receiving anything.
Yes.
And that's the reason why it took us a while to figure it out. Any other questions?
Oh, thank you.
Thank you.
Hi, my name is Eduardo Williams.
My name is Arnolfo Barreco, and we're going to introduce you to passive wireless pavement sensor.
And our advisor is Dr. Ferry Farman. So basically, the problem that we're trying to solve with our project is to have data to be accessible based on the road condition to people. There's products out there that they do this, but it's more expensive and they use more equipment. And what we're trying to do is to bring this information to the user as a way to inform them about road conditions.
Yeah, so one of our main goals was to make our system as small and simple to use, so just plug and play. And we achieved this by using a GPS to gather sensor data.
Well, this quote I found when I was researching other systems is that people are actually investing on such systems to give them information about the quality of the roads and how to actually grab this information for their own convenient use. Yeah, I'll talk about that. So there's two similar products out there. The first product that I found there is actually a mobile pavement management system. And as you can see, this system is bulky. It uses a lot of software, a lot of technology that a common user will not even know what to do with. And the thing that they have is a GPS, a high-speed laser, and it's company-owned, and it's complex and expensive. And the other similar product that I found out on the internet was this microstrips that use fiber optics to actually sense the road deterioration. Also, this is company-owned, and it's complex and expensive as well.
So the 10 features our system includes is a GPS module that collects speed, location, time, and latitude.
And our second feature is the SD card module. Will save GPS data and system data as one single point.
And it includes a geophone sensor. That's the type of sensor we're using, and we'll discuss a little bit more about how that works.
And so our product has a base station. So basically this is what the user will actually be holding and see the data going through. So we need to display with an LCD speed, location, time, satellite data, and the actual sensor data that's coming through.
So our system has 3 parts, and one of the parts is the base station, which includes a LCD display. It has the GPS in there, and XB to receive the transmitted data. Also SD card slot that we will save basically all our data there.
And the other part of the project is the node sensors. We have 2 node sensors. Also, they're connected to 2 XBs that are transmitted to the base station.
And like we said, every node sensor has a geophone. That's how we are detecting the pavement.
And we're using MATLAB, and we're using a interface function that actually help us use Google Maps and use our data to actually map our information in as a visual aid to other people.
So once we have gathered data, the purpose of this was to create some thresholds that we could work with. Basically what we did is we gathered data points, and then we basically just put some thresholds. Therefore we got the high end of the geophone sensings and low end and medium points. We'll show you guys that in our test results.
So basically this is our block diagram. The knowledge behind it is actually pretty simple, but still complex enough to actually make this a good project to do. So basically, the system starts in the base station and initialize the GPS, the XB, the SD card, and the LCD. And the base station is actually governed by the GPS. So it eventually has to wait until it gets a fixed location. So once that location is fixed, the GPS data sends an OK to the Arduino, and then it starts collecting the data. If that fixed location is not an OK sign or flag, it's gonna go back and it's still gonna wait for a fixed signal. And it's gonna do that until it actually gets actual, not a corrupt data, but actually the data that we're looking for, so an 100% data collection. And then after we get the actual data that we want, it's gonna be transmitted to the XB from the 2 sensors, and then it's gonna unpack the XB package and extract the value that is coming from the 2 sensors. And then it's gonna be saved into an SD card that we can use to actually extract the data and use it in MATLAB.
The node sensors work similar. Basically what we're doing is we initialize the XBs. They are ready to start transmitting. Now both of them will transmit 2 sensor readings. One is a geophone, one is a temperature. We've attached the temperature just to show that we could, besides sending a geophone sensor reading, we could also attach another sensor. Therefore, this gives us the capability to add more than 1 sensor. But essentially what it does, it makes sure it's just sending sensor readings to the base station. So as soon as the base station is ready to pick up that package, it will be transmitted. And it keeps doing this for the remainder of the time that it's on.
So basically, this is our finished product. During this time when we took this picture, it was running, and as you can see on the screen, we actually are getting latitude and longitude, and we're receiving data points from the 2 XBs. So this is basically this is the base station schematics. We have an LCD screen, XB Series 1. And we also have a power booster converter. So basically, we can actually power this through a USB or actually a battery pack. We have a micro SD card, and we have a GPS sensor. The reason why we went through with this type of microcontroller is because it has multiple peripherals that we can actually access. And the two things that we were looking for was to have SPI and also have IC2 to communicate with the two devices. So something about the base station that is really key to the project is that the GPS is refreshing every 1 kilohertz. So it's getting information like every microsecond. Also, it's saving it through an SD card that eventually we're going to use to manipulate the data. And the reason behind it has 3 to 5 second delay is based on the schema, the block diagram that we went through. Is that it has to wait until we get the exact data that we want. And for example, the bottom picture right here is an actual sentence that the GPS receives. So we're logging 4 points. Basically, we're logging time, a real-time clock, latitude and longitude, and we have speed and signal strength. So the more we put on the sentence, the more time it has to wait until it gets the fixed location. And we're using SPI to communicate with the GPS, and we're using IC2 to transmit to the SD card.
Now here's the schematic for the node sensor. Like I said, both node sensors are identical. So basically we have a power booster that will power, being powered by a battery. And it will power the Arduino, the XB, and the geophone is, it does not require any type of powering. It produces once it's shake, it produces a voltage that the Arduino will read. So this is a package timeline, transmission timeline. Basically, both nodes will be transmitting at a 1,000 milliseconds, and the master, the coordinator, that's basically the one that's gonna decide which packet or at what time to receive that packet. First, what it's looking for is for the package coming from node A. Once it has, we've done if statements. Basically, if it's receiving a negative temperature, that means it's a corrupt data point. Therefore, we will not record that. It would keep looking for the next positive value. That would ensure us that that geophone sensing is not corrupted. So it will do this until what you have to keep in mind is that it's the coordinators more or less being governed by the GPS. So as soon as the GPS has a fixed location, it will start looking for node A data collection and then proceed to node B. That's basically how the master coordinator works.
So basically, this is our test result, and this is the most accurate test result we have done. This result is basically 3 runs on the same route that we went through. And we'll come back to this picture, but right now we're going to talk about the ranges that we actually went through to actually find this point. So this map shows the high points. It ranges from 15 to 45, and this scale is based on the actual range of the geophone. When it goes through when it goes to the node sensor, it goes to the microcontroller. The microcontroller actually gets the resolution based on the 8 bits that it has with a 1 point microvolts that it has. So basically, that's the resolution that we actually get. So when it transmits, we only get solid numbers. We don't get like any fraction or any decimal. And these values are based on how the road condition is is based on. So if we go through a pothole, we're gonna get a range of 45. But if we get a, can you change to the one? So we get to the low one, this is the medium to low, we're gonna get a range from 0 to 15. So what we did is just to put the medium and the low together because it doesn't vary that much, but it's still considered a road condition. So basically this is when we put the two maps together. As you can see, well, I don't know if you can see from there, but there's points or there's clusters on specific locations on this map. And this is based on the common points that the geophone and the GPS actually logged in their points. And we chose this map specifically, or this route specifically, because most students at the SSU or anyone that goes through this campus, they know exactly where all these points are. Like we went through the back of the school where the constructions are, and exactly where there was this pothole that the construction area was going on, it receives it, and it was actually accurate enough to measure it like a meter apart from the other one. So our test points were really close to each other. So it means that the more runs we go through the same road or the same point, the more clusters we're gonna get, and the more specific our data is gonna be to show that there's a road condition there. And basically, we have an actual run video that we had, but we can actually show that like after. But it actually is reacting to the base station and to the road. So we can show that later on.
Another thing to point out is the where you don't see the dots or any dots. That's because the GPS had not locked any coordinates for that. So how we would fix that is just, so this was done 3 times on the same route. So by doing multiple runs on that, so say 10, we would get more points. So that's how we would fix the no points on some of the areas of the route.
And also, like to add to that is that we are losing points because of the data that we're extracting out of the GPS. So if we just grab the latitude and longitude and just ignore the other ones, we're gonna get more frequent fixing. So that could solve this problem. But also we can do it by increasing the refreshing rate on the GPS. So mixing and matching those two, we can actually get like more accurate data through one run than actually 3. So that's also a part of our test results, but this image right here represents a good test run and a good outcome of what we're looking for. So basically, this is what we extract out of the SD card. It's just data points, and by using Excel, we just managed just to clean it up and use this file to put in through MATLAB that has an algorithm to actually arrange the ranges that we tell MATLAB to actually separate them. And it's done by like getting the high point or the meter point and associate it to the location. So what we're doing is just plotting the longitude and latitude with a reference on the geophone sensor.
Now here are some of our learning outcomes. Me personally, I learned how to make this is a simple XP network, but you could essentially make a bigger one. Once you have 2 working, you just keep adding with similar configurations, and you'll get a bigger network by that.
And also something that we learned, and it was parallel to one of our classes, ES310, is that we found different communications that we can actually interpret the serial communication. So we use SPI and IC2, and this type of this information was actually given us recently because we were just taking it on this time. So that's why we went with the Arduino base, because we were more familiar. But if we go to like let's say a PIC now that we're more familiar with it, this type of protocols will be more implemented because it's more on the programming side than actually just grabbing libraries and just manipulating it. And also the GPS is something that I really learned and I'm really interested into, because there's data that's coming us every single time, and we don't know that we can actually extract that data and tell us so many things about our location. And I learned one thing, that the GPS signal doesn't only transmit one signal, but actually transmits 4. And those 4 signals represent different parts of your location. And it's pretty interesting that with just one little device, you can do a lot of things, and you can record a lot of things that you didn't even know that was out there.
Another thing is time management. Everything is possible. You just have to know how to manage it. I think that's one of the biggest things we've all learned from that. And another thing that kind of ties in with that is you have to give enough room for debugging. I heard this from the beginning, that debugging is the one section that takes the most. Now I could see that it's very true. And that's one of the advice I would give to anybody else doing the senior project next year.
And also, the last point is like, it's not the same as just thinking about it. And we heard this like so many times, that if you just think about it and just don't do anything, like, and just keep it in your mind, not actually implementing it, it's much harder than it sounds, because a lot of things such as debugging, parts that are not connecting, or anything that you think is simple, it's not. So it's something that we learn, and we paid for it like a lot, and it's something that we're always gonna have in mind. And some events that we attended was the symposium last night and Market Day, and some feedback that we got out of this is that most people are interested on our prototype because of the simplicity that it has and the outcome that it could provide to the potential consumer. And we actually found, well, not found, but someone approached us, and it was a motorcyclist enthusiast, and he said that this type of system he can use, and I don't know if you were there, but he actually said that once we're finished with our product, he can actually use it for his club that he has. So the thing is that he said that bikers are new to biking. They don't know the roads, but if we have something that actually tells them like what's going on ahead, they will actually be more prepared and not make the mistakes that a rookie will do. And it was pretty like refreshing and pretty like, I don't know, accomplishing that our simple project has more potential than we actually started with. And you have something else to say?
Just the exposure that we got at Market Day and the research symposium. I think that was very valuable. We got, like Eduardo said, a lot of input. We didn't know, we kept it to road condition, but how Eduardo was saying, this could be used for many other things. Another person that approached was talking about, instead of something similar to how Google does it with traffic, so they would tell you how congested that route is. So what we could do is see how many potholes you're going to encounter, how bad that road is. So maybe you could take an alternative road. That kind of ties in with what we wanted, but this way we kind of heard it from somebody that actually thinks this would be useful for them in their daily commute, and I think that was very rewarding.
Yeah. So our mentor is one of the most reliable persons that we ever met, and it's Dr. Faridi. And it's not being kind of like because it's our mentor, but it's actually he gave us a lot of ideas, guidance, and also sometimes he destroyed our ideas and we have to rebuild it back again. But that is the actual process that is out there, Management is gonna tear your ideas down, and you have to just build it back up. And it's something that is really important. If we didn't get anything out of this project, it's that idea of how to create a concept into a product is really rewarding. And having Dr. Farid as our mentor, and also he sponsored us with parts and his help. But besides that, he's like the most generous person I ever met, even though he was kind of harsh sometimes, but I can live with that because right now we have something that we can show for it, and that's the most rewarding part of this project we've done. And also because we didn't took microcontrollers like a year ago, and we're taking it right now, Dr. Farid gave us a lot of insight of how to actually approach this in a different way. And maybe it's like 75% of our success that he was our mentor, and we gave you thank you for it.
So our learning experience, this is kind of more of a personal thing. It would be we learn how to actually package something, make it more deliberate, more friendly to users. We are all engineers. We know how to talk, I don't know, schematic wise, but we need that real approach with the real client. I think that's one of the great experience that came to me.
And something that I thought it was not going to be an issue, but it actually became an issue, was communication with partners. Even though that I know my partner for like a long time ago, it's really hard to actually bring an idea, and that idea could actually potentially destroy his idea. So it's actually, we were toggling back and forth, but like we said, it's part of the experience, it's part of working with a group. And as a cumulative time effort to do this, we spent almost 500 hours in and out of school. And for my personal use, after this project, I'm gonna be looking more to GPS and making it even smaller and more compact for better use. And
another thing I would like to add is staying committed to your project. I think that was, when you run into any trouble, you kind of second guess yourself if you really want to continue. I think we all run into that, especially when things are not working the way you want. But staying true to your project and just trying to see the outcome of it, I think that's, we have it here and it works. I think that's very rewarding. So yeah, two heads are better than one, but only when they think alike. So like Eduardo said, thinking the same way was hard. Just clashing ideas, but we made it work, and that's all that matters, right?
So yeah, we can go to the website right now because we have our demos, because the GPS doesn't actually get a fix here. So basically, this is basically running the GPS with the two sensors. Right now it's being fixed with the longitude and latitude. And also something we missed to say is that the base station has two menus. The first menu is just the location, and the second menu gives you the time, speed, the altitude, and the connection between the satellite and the GPS. You can also go to the other ones. Go to the test results. Yeah. Full run test. So basically, this is our full time, our run around the perimeter that we're going, and we were running through a lot of construction area, and actually the system picked that up when we were doing it. So this is like a 6-minute video around that route 3 times. And go to another one. Well, we can show the poster pictures. But anyways, go back to the presentation.
Oh.
So some future work that we want to do, actually I started doing already for my 310 class, is actually interfacing the PIC 18 with a GPS. This guy took at least 2 weeks to actually make it work because the PIC, you have to actually make your own libraries and everything that actually the Arduino makes this easy. So as a prototype right now, it's actually working like 50% right now because there's no more work to be done. But actually, that was the stepping stone before an Arduino to a PIC. And this brings packaging even smaller and cheaper than what it is right now.
So this would reduce our cost, just package even smaller. And essentially what we want to do is move into, instead of using 2 sensors, use 1. And we would actually try to implement another type of sensor, not the geophone, comparing it to the accelerometer or another high-end, better sensor. We thought it would be a better thing to do than to use our geophone that we have been using.
And also something that we want to add to our future work is that instead of having a base station, we can actually have a phone instead, so we can actually log into the internet and we can just dump those points into a map, and that map can be seen for other people. So the potential of this prototype can actually be extended to more people using it, and having a wireless or a internet connection between our sensors and the users is pretty promising, and I think we're going to pursue that a little bit more because the concept is actually more like the people want something like this in their cars, and why not give it to them? Yeah. Oh, and this is like our sensor location. Basically, we have one of the sensors mounted on the dashboard, and it's kind of weird, but actually, we can attach them to the window, and we get better data with it. And at first, I was kind of not really in favor with this, but actually, it works really well because the sensor is actually resonating with the window, and it actually makes it like a small amplifier, and we get more resolution based on that. And we have our reference sheet in the back. But
questions?
Besides that, any questions? Yes?
Frank?
Did you, what's the voltage that the actual sensor nodes are running on?
The sensor, like the nodes are running, well, we have a power regulator that takes in 5 and puts out 3.3. So the 3.3 is running the microcontroller, and the microcontroller is running the XP, and the XP is just sending the data.
Yeah, you might want to add to your future works to change it instead of 5 volts to 12 volts because most cars run off 12 volts. Yeah. So that would be an easy wire job.
But the thing is that the base station actually has a USB port, so we can just put it right into the, where the charger is. And actually we have
for the like sensor nodes.
Oh yeah.
Because you would mount them somewhere else in
Yeah.
the car.
If we want to make the sensors permanent, then yes.
Yeah.
But as a test, right now we want to make them more modular and more simple to move around. But yes, it's part of. If we want to proceed this, make it more stationary, then yes, we can put it as a 12-volt regulator. Yes.
That's an interesting project. The thing that I want to say is that with the experiment that you made and so on, did you find any way as how to summarize the data so that it would be useful? Because you can certainly get a lot of data when you go a couple of times and so forth, and then the data may not correlate with each other. So somehow there needs to be a summarization algorithm so that you can just interpret the data, and then people who work in the city, need to understand this thing and make it useful.
Well, part of the issue that we were running through is that the two XPs they're sending their data in a different time. So basically we're grabbing one information like 1 second and 1 second later. So actually making those two actually match right now is kind of hard, but our algorithm right now for the math lab is that it's just taking an average, not an average, but actually they're comparing it to the next one. So what you're saying is kind of like our next step towards that, because we want our data to be easy to access and just eliminate that part right now that we're having issues. But probably that's going to be more into software based, and we can work on that a little bit more.
Anything else?
Other questions? Okay, thank you.
Yeah, thank you.
Okay, so this pretty much concludes the presentations. I just wanted to point out a couple other things. Please return Sharon's pointer. That's the most important thing that I have to mention. So if anyone has it, please. Oh, okay, this is the one, right? All right, that's very important. The second thing is, please revise all the feedback or comments that you have received for your documentation and return that prior to probably before next Friday. All the recommendations, all the comments have already been made. I just have to give you permission to the folder so you can see everything. So I'll do that right after the presentation. If you have any questions, please, each of the comments, each of the folders that's been created, it has the name of the reviewer. So if you have any questions, you don't understand something, please contact them and ask them what they mean by the comment that they have made. Also, we just checked a few of the web pages, and seems like you haven't had a chance to completely update your web page. I know you've been busy, but please make sure all these slides plus the latest version of your documentation goes there before Friday. With that, thanks again. I know you have spent a lot of time. It was really great to have all of your presentations were really good. And let me know if you have any questions. Thanks again. So.